Alrighty, welcome back to operating systems. So we get to discuss file systems now. So me telling you I was curving down on the midterm, I didn't even scan them yet. That was a joke. It's fine. So all the midterms scanned as of this morning. TAs are doing that. They're grading as we speak right now, so hopefully I'll get back to you sooner rather than later. Usually the turnaround time's pretty quick. They're grad students, so they're kind of like you. They're nocturnal, so they'll probably grade at night and on the weekend and things like that. So hopefully it'll be done by Monday. We will see. Usually they're pretty quick. So now we get to talk about file systems. So we've all used file systems before. This is probably somewhat of a review, but the layout in POSIX looks something like this. There is actually a standard called FAS, which is the File System Hierarchy Standard. Very, very creative name. So the File Hierarchy Standard says that everything must begin with a directory called /, and that special directory is called the root directory. So that root directory, it has to have a bunch of other folders in it or directories, and according to the standard, it says what should be in those directories. So there's supposed to be a bin directory that has all your binary files, all your programs, all your executables, things like that. There's a dev directory that's supposed to represent all the devices on your machine. Typically the kernel will represent all of them. So this will represent things like your hard drives and things like that, because everything is a file. ECE, which will generally have all your configuration files. Home directory that will have a directory for each user on your system. So if you're using the UG machines or something like that, you'll have your own home directory. Might be in a different location, but it follows the standard. For me, it'd be something like home/John. Inside of it would have some files, so for example, to-do.txt, and then there's also this mount directory, which should have things in it, like when you plug in a USB drive, it should be created in this mount directory. So all of our processes will also have a working directory. So currently, if my working directory is /home/John, well, we have a little bit of practice or hopefully some experience with absolute and relative paths. So if I was in /home/John, what would I need to type to get to to-do.txt? Yeah. So it's a file. Yeah, so if I wanted to access it, or just its path is just to-do.txt, or have we all encountered the special dot? What about if I started with a dot? If I started with a dot, what would it be? Yeah. Yeah, /. So dot is supposed to be this current directory, so I'm currently in home John. It's a file in there, so I could do /. What about if I'm in home John, what about the relative path to this USB directory? Yeah. Close, yeah. Yeah, so if I'm in John, if I do .. that should be up one directory. So I could do .. which brings me to home, then /.. again, which brings me all the way to root, and then /mount/USB, which is longer than absolute. So absolute paths start with that root character always. So starting at root, how do I get to to-do.txt? Well, it should probably just be /home/John to-do.txt. And to get to USB, it would just be /mount/USB. So any questions about that? All right, so there they are, our special symbols, which you will discover what they actually are in lab 6. They are not actually that special, but they are actual entries in your directory. So there is one called dot. Dot is the current directory, and dot is the parent directory, or one folder up. So this is where it comes into fun history land. So have you noticed on like Linux systems, you can create hidden files if you just start them with a dot? Anyone know why that is? So, whenever you type ls, typically you don't want to see dot and dot dot, right? So if I wanted to ignore them, if I wanted to ignore just those, I'd be like, well, if the directory is dot or dot dot, just don't show it. That's not efficient. So some smart programmer was like, well, I can make this a lot easier. I can do it in one line of code. And his one line of code was just, if it starts with a dot, which covers the case of dot and dot dot, then just don't show the directory. And then after that, oh, guess what? Well, if you just named a file starting with a dot, it also wouldn't show. And that's how hidden files came along. Someone was trying to be clever, and that bug became a feature. So that is literally a case of bug becoming a feature. So if you're on Linux, you can thank a lazy programmer for making dot represent a hidden directory. The other special one is this tilde character, and that's always the current user's home directory. Might be in this environment variable called home. And relative paths are calculated from the current working directory, which is given by this pwd, or print working directory, which is a property of the process. So, for files, so far, when we've opened them and read them, we have only read them and wrote them sequentially. So, for sequential access, each read just advances the position within the file. So if my file has the contents hello world, and I read a few bytes from it, I would read hello, and then if I do another read system call, it would continue where it left off, and I'd get world or the remaining part of the file, right? That's how we've been using files so far. Anyone disagree with that? Because things probably will get weird here. So how writes happen? Similar way, but they're just appended to whatever the position is, and it's updated afterwards. So if I open a file and I write hello to it, well, it would advance the position, write those 5 bytes or however long it is, and then if I do another write system call to it, it will just append it to the end of that and keep on going, and I can grow it on and on and on and on again. So you can also access a file randomly, so I could just open a file and go to any old random byte and start reading that, but we don't know how to do that yet. So luckily, there is a system call for that. So here's our friend open. So open takes a whole path name, flags, so if I want to open this file for reading, for writing only, for reading only, if I want to open it for reads and writes, whatever I want to open it for, those are all the flags. And one of the other flags you might be able to put on is this append flag. So that will move the position to the end of the file initially. So if I just open a file and then I write to it, by default, I'm going to write to the beginning of the file. I'm going to overwrite whatever was there before. If I open a file with this append, and then I do a write system call to it, it will just append it to the end of the file, and I'll just grow the file. So there is this lseek system call in order to change the position that I'm going to read and write from the file. So it takes a file descriptor that I want to manipulate, an offset, which is just the number of bytes from the position that I want to go forwards, backwards, or stay the same from. And then the third argument is this whence parameter, which is basically just a slightly scuffed C enum. So it has 3 choices. It can be seek set, seek cur, and seek end. So if whence is seek set, that means the offset you give is relative to the beginning of the file. So it's absolute. So if I have whence equal to seek set and an offset equal to 0, that means go to the beginning of the file. If I have it seek set and then offset to 16, that goes to the 16th byte no matter where that position currently is. If I set the parameter equal to seek current, that offset will be relative to wherever I am currently at in that file. So if I'm in the middle of that file and I want to just back up 4 bytes, I can set whence equal to seek cur and offset equal to -4, and I'll just back up 4 bytes. And then similar to seek end, I could set to seek end. If I set the offset to 0, I go to the very end of the file. If I set to -1, I go to the second last byte of the file, so on and so forth. So any question about that? Because this, basically there's an internal position of where to read and write from a file, and things will get weird. Yeah.
What is the second argument?
The offset. So based off this whence, it's where I'm going to move the position to. So it's just the number of bytes to move it depending on what this whence is. Yeah.
But like, let's say you do seek end and then you supply 1 to the offset, is it going to move it 1 after the end?
So you have to move somewhere that's valid within that file. So if I do end and then 1 that's beyond, it'll probably give me an error. Or maybe if I'm lucky, it'll grow the file. Probably it'll give me an error. Pretty sure it gives you an error.
Okay, so it's 1 after, it's like whatever offset after where you put your...
Yeah, so depending on what it is. So if I do seek set, so that's relative to the beginning of the file, and I do negative, it'll probably give me an error because I'm before the beginning of the file. Yep. All right. Any questions with that? So basically there's a position. It's going to get weird once we bring fork into the picture because guess what? Fork is always in the picture. So this is what we did before. So you get to explore what a directory actually is because internally this open dir C wrapper, well, that will open a file descriptor, and a directory just is a file descriptor like anything else. It doesn't open system call, but C tries to, or the standard C library tries to abstract it away. We did this in your lab, was it 1, I think? So you're going to figure out how this actually works as set up for lab 6, and it will be cool. But for that, we need to talk about what is in the process control block and what a file descriptor actually is and be a bit more explicit about it. So each of your processes in the process control block will have a file table in it. And so far I just said think of that as just a pointer to a file. Now we get to figure out what it actually is. So for each process, it would have a file table, and it would point to things, but it doesn't point to just a file, it points to some other information. So for instance, in process control block 1, file descriptor 0 points to a position, so that's what lseek will manipulate, where I currently am at in that file, some flags that I used when I actually opened the file, and then a pointer to a vnode, which sounds a bit weird. And what that represents is just anything you can read and write bytes to. So this can represent, a socket, a real file, a pipe, can represent a whole bunch of stuff. They just, in order to abstract it, well, they just called it virtual, and it's anything I can read and write bytes to. So in lab 6, we will see what the structure is called. Well, we'll actually do that in the next lecture. So if this vnode represents a real file that is on the disk, well, it's actually called an inode. And we'll see what an inode is in the next lecture. But for now, we'll keep it as a vnode. So this vnode points to the actual file that I want to manipulate through this file descriptor. So you might notice things get a bit weird because also in process 1, file descriptor 1 could point to a new entry in this table with its own position, its own flags, and its vnode could point to file B. And then I could have another process, process 2, and its file descriptor 0 could point to a completely independent entry here with its own position, its own flags, but this vnode points to the same file B. So that way, one process does not interfere with the other process. So that position, if process 2 changed the position, it wouldn't affect process 1. Even though they're actually accessing the same file, they could be, if they do a read, they might actually read different bytes from that same file, still go to that same file. So any questions about that? All right, so a file descriptor, all it is an index into that table, and the kernel will keep a global system-wide open file table, sometimes referred to as a GOF, because GOF, why we called things what we call them, we're just not creative. So the GOF holds information about the position, the flags, and then points to a vnode, and that vnode just has to be something that actually supports reading and writing bytes to. So the vnode holds the actual information about the underlying resource that it represents. So it could represent a regular file, which we'll see how that's actually laid out. It's called an inode, next lecture. But it could also represent pipes, network sockets, shared memory sometimes. Anything else we used as a file descriptor in this course? I think that was about it. Anything to read and write bytes to. I think that was pretty much it that we've encountered so far. Yeah. All right. So now we have to talk about forking, because this will get slightly weird, slightly maybe not weird. So when you fork, it's the exact copy of the process. So that whole process control block, you get a copy of it. So specifically for us, that local open file table will get inherited. So it will just get copied. So you will have, that's why all your file descriptors are the same numbers and they point to the same thing. We just weren't super clear about what they point to. So we said they point to a file, which was kind of true, kind of not true. So they do eventually point to a file, but they also have a position and some flags, which are stored in the global open file table. So in this case, this is what happens when you fork. So if I fork and process 1 has file descriptor 0, and it's pointing at this, so always to the left here, within the process control block, these are local open file tables, and in the middle is the global one that the kernel maintains. So in this case, process 1 and 2 point to the same entry, so they'll be sharing that position. And they also, that entry also points to file A. So now this is what it would look like after I fork, in which case they're sharing that same position. So say I had 2 lines in the file. What would happen if process 1 and 2 both did a read system call? What could each process see? Yeah. Yeah, it kind of depends on how many bytes, but is it ever the case that both processes will see the entire file? No, because they're sharing that position, right? So it kind of depends how much I read. Since they're sharing it, well, if one of them reads, it could read the entire file, in which case it would update that position to the end. And then if the other process tried to read it, it would get read of 0, saying that you've read everything from the file, nothing else to read. So one process reads everything, the other process reads nothing. Or it might be in the case where one process reads 1 line and then another process reads the other line, and you get like half and half. Or it might be any combination of them depending on how many bytes you read and write to, which seems like an odd behavior for forking, but it's actually been useful so far because, well, guess what? When you fork and you're sharing, standard out, standard in, and everything for your terminal, well, this is actually the behavior you want. If you type A, you don't want every single process to actually consume that A and do something with it. It's only the one you're typing in. So only one of the processes should actually consume what you've written instead of every single process that got inherited along the way. So might seem weird, but this is actually useful. So any questions about this one? Although if it represents a real file and then you only read half the file, that might be like kind of hard to debug. And in fact, I guarantee at some point in your life, if you take this course to heart and you're forking, you'll probably encounter this problem, and where you're trying to access the same file in your forks and they're actually sharing the position, and you're going to get some weird results, and then you're going to have to remember this lecture and be like, oh yeah, crap, I should probably just reopen the file. And that way I have my own independent position. So whenever you do an open system call, you'll always get a brand new global open file table. The only way to share an entry is through forking. All right. So yeah, yep.
I guess this also applies to pipes too.
Yeah, so pipes are just the exact same thing. So a pipe would have a position, some flags, and then that V node would just point to the actual pipe. So,
So if one process is like reading pipe,
yep,
it reads 3 bytes,
yeah,
and then one other process that also calls read the pipe, starting from pipe 4.
yeah, a different 3 bytes. So this is the same thing as if it represents a pipe. So if I create a pipe and I have 2 processes and they both call read on the pipe, I don't know which one's going to read information, but they're not going to read everything I put into the pipe. So one might read a little bit, one might, you know. So you won't get any duplicates, and it's kind of like a data race. Well, it's kind of just non-determinism because you don't know, because essentially it's whoever calls read first, which is up to the scheduler, which is fun. All right. So yeah, just remember, if you fork, you're sharing that position. And also, well, other fun things that could happen is because you're sharing that position, that lseek system call that updates the position, well, it would update it in your parent as well because you're pointing to the same entry, so any change to the position would be shown in both processes. So you could really screw with your parent if you want, just kind of like in real life. So you could fork, since you have a copy of all the file descriptors, you can just throw it to the end of the file and it won't read anything ever. If you want to make people not be able to debug anything ever, you can start doing that and get some job security. Because, yeah, they probably don't know how that works. So, yeah, and if you open the same file in both processes after forking, then, well, you have 2 independent entries in the global open file table. They just point to the same file. So let's see if we can do this. So given my program is something like this, I open, so say it has no file descriptors open for whatever reason. If in my process I do open to-do.txt, I fork and I open b.txt, how many local open file tables do I have per process? And then how many global open files do I have in total? So I will give you a second to think about that, and then we can go over it. All right, any guesses? Yeah.
2 local per file.
Yep.
And 3 globals.
Yeah, so 2 local per process and then 3 globals, right? Everyone get that? All right, I won't even draw it then. So I'll just go to the next slide. So in each, well, actually, no, I'll draw it. So if we have process 100 that starts executing, well, it opens to do.txt, which would make a new global entry. Whoops. So as part of the global entry, it would get a position, get some flags, and then a pointer to a V node. And then that would point to to-do.txt. Wow, that's great writing. Well, let's call it to-do so I don't try and cram it in. So in process 100, well, file descriptors will just do the lowest index first. So it would have file descriptor 0, and it would point to this entry. So now when we fork, we create process 101. And process 101 will be an exact copy of the parent at the time of the fork. So it would also have the exact same local open file table, which points to the exact same global entry. And now after the fork, I don't know which one will execute. In this case, it doesn't really matter. They will each create a new entry in the global open file table with its new position, new flags, and then a V node, which points to b.txt. And say process 101 open first. So file descriptor 1 would point to this entry, and then eventually If process 100 executes, it would have its own unique position, its own flags, and then its own vnode. And then this vnode would also point to b.txt, and it would get its own local entry 1. So any questions about how that works? So now both of these processes, well, they can read b.txt its entirety because they have their own position, but they're sharing file descriptor, they're pointing to the same global entry in file descriptor 0. So if they both tried to read from it, they would read some bit of the data and they would update that position, and then the other process, if it reads, would just carry on from that point. So any questions about that one? So that's really what file descriptors are. So that position will become, it wasn't really important before, but once you start moving around and stuff, it will become important, especially if you're trying to, if you start creating multiple processes and then you're reading from files that were already open, this, I guarantee, will surprise you. So this is why it's in this course. All right. So now we need to go back to file systems and how we actually store files. So in this case, we kind of looked at what an SSD is. It has a bunch of pages, which are like 4 kilobytes. The generic term, usually we refer to them as blocks because they might not exactly be 4 kilobytes. They might be 8 kilobytes or something like that. So we just have blocks of storage we can use that will be like 8 kilobytes or something. So given those blocks, we have to be able to form those blocks all together to form a file and describe our file. So in this case, each box is a block. Say it's like 4 or 8 kilobytes, something like that. And I have a green file, a red file, and a blue file. Now, if, let's say we give the green file a name, just call it like the green file. How would you describe to me where this green file is on this disk? Yeah. Yeah, the first 3 blocks. What about the red file? Kind of looks like an array, right? How do you describe an array? Yeah. Yeah, starter end or starter how big it is, something like that. Because it's all contiguous, you don't really need to tell me that much. Just start how big it is. So if I was to describe this green file, and these are all blocks that are in order, I could say it starts at block 0 and it's 3 long. For the red file, starts at block 6, index 6, and it's 6 long. Blue file starts there. So fairly concise way to describe a file. What about if I want to make the red file bigger? Yeah. Yeah, well, I'd have to move it, or I could move the blue file if I wanted, but I just have to get it out of the way because everything needs to be contiguous. So moving files, this might actually suck for that. You would especially not want to do this if that red file was several gigabytes and you're trying to add a little bit more. And then you have to move a gigabyte, and then you add a little bit more, and then you have to move it again, and move it again, move it again. Probably a bad idea, especially since files are generally big. So it's space efficient if we want to describe a file because it's like an array. You only need to tell me the starting block and the number of blocks we need to store it. It's got pretty fast random access. So say I want to access byte 10,000 of the file. Well, since everything is contiguous, it's like an array index. That calculation is really, really fast and really easy to do. In this case, what block it is on is just whatever the offset is plus the block size, and then you take the floor. So if they were like if blocks were like 8,000 in size, and my block and I was looking for byte 10,000, well, it's not going to be on block 0. It's going to be on block 1, and I could just do that calculation for any offset. No problem. But This is kind of bad. Files can't grow easily, and we have to talk about fragmentation. I think it's the first time it showed up in this course. Whenever you see the word fragmentation, usually has to do with storage or memory, and it basically means wasted space. So internal fragmentation, it's relative to the blocks. So internal fragmentation means I'm wasting space within a block. So for instance, if my blocks are 8 kilobytes and I need to store a file that's only 12 bytes, well, I still need to use a block to store that file because I can't do anything smaller than that. So all the other bytes aside from those 12 in that block are essentially wasted space. That's what you would call internal fragmentation. What you call external fragmentation is wasted space, wasted blocks, or anything between blocks that's wasted. So in this case, let's say I made the red file smaller by 1, so there was just a hole of 1 between the red file and the blue file. Well, that space is going to be wasted if all my files are bigger than a block. I can never fill that hole up. It's just there forever, just wasting space. So that's what external fragmentation is. And it becomes a problem, especially once we go later and talk about memory management, or basically how malloc works, because malloc has the same issue as this. All right, whoops. All right, so if that isn't great, well, how can I store a file slightly better than that? So I kind of ruined it already. So I could just store the file as a linked list. So we like linked lists, or at least evidence seems to say that from like lab 4. We kind of like linked lists. So we could store a file as a linked list. So this green file, now it doesn't have to be contiguous. I can just, given a block, I can just point to the next block in the file, and then eventually it'll end, point to nothing, and then I know I'm at the end of the file. So if I was to describe this green file, what would you need to tell me to describe the green file? So think of like a linked list. Where do you have to tell me about a linked list to describe the whole thing? Yeah. Yeah, well, at the end of the day, just where the head is, and then I can, if you know the structure of the linked list and where the pointers are, you can figure it out from that. But to describe this, I could say, hey, the green file, well, you know where the pointers are. The green file starts at block 0, just follow it. Any disadvantages to this? Yeah. Yeah, real slow access too. So what if, if I wanted to go to block 5, well, I have to start at the beginning, keep on going all the way to block 5. And why is this also especially bad? And hint, the answer is performance. So in this case, I store the pointers on the block itself. So yeah.
Is there a way to the cache somehow? Because you're like going back to the shared memory, so you have to like reload the cache?
Yeah, well, in this case, typically you cache like blocks at a time, but each time I access a pointer, if it's like this, it would be a new block which would not cache, right? So every time, if I want to go to block 4 of this file, well, I have to go to block 0, that wouldn't be in the cache, read the whole thing in, and now I read in like a whole block. But, to figure out the next one, I just read the pointer from that, have to go to the next block, read the whole block, and it's really, really slow. How would I speed that up? So if pointers on all different blocks is bad, where can I put the pointer? Can I put the pointers closer together somewhere? Yeah.
Maybe you can store like a separate data structure, just one already, one place to one, so that you don't have to like traverse through and look at it while you're searching.
Yeah, basically, yeah. So, yeah, well, I could basically just take all the pointers away from the blocks and just shove them all together, right? Just shove them all together so that way it kind of sucks, but if I have to read one, well, hopefully I cache the rest of them. They're all in the same block. I don't have to reread it again. So this linked allocation, really slow random access because it's a linked list. I have to keep on going through things. But it's kind of nice because I can grow and shrink files really easily because one block is as good as any other block. So I don't have any external fragmentation, because if there's a one gap hole, that's fine. I can just point to it and it can point to another block. Doesn't have to be contiguous. And that last question there, to increase random access, yeah, well, if they're not cached because they're always in different blocks, just move the pointers all to one single block so they're all beside each other. So that's our first file system that's actually used. So same idea, but it just takes all the pointers and throws them all in a block, or throws them all in just a giant table. And that table is called the file allocation table. Have we ever heard of a file system called FAT32? This is FAT32. So FAT32 means file allocation table, and the size of the pointer in this block is 32 bits. So that's what it means. Every entry there, that represents a pointer, it's 32 bits. That's what FAT32 means. If you use Windows, you're using FAT32 even if you don't know it, because that's the file system that Windows boots off of, and it has to be that, and you're definitely using it, even if you don't know it. So if you open up Disk Explorer or whatever the file manager, whatever the hell it's called in Windows, and you look at your drive and how it's formatted, you will find a FAT32 partition, or it might be called a system partition. It's this. So what's kind of bad about this? Yeah. Yeah, you need more memory. Well, in that case, all these pointers would be like on a block somewhere, but the size of that table depends on how big my disk is, right? Which is kind of bad. So if I have a bigger disk, I need a bigger table. So it doesn't really scale that well, because it gets worse and worse the bigger your disk is, and that's why it's only used, it's simple, but that's why it's only used for like your booting drive, because it doesn't have to be that big, and that file allocation table doesn't actually have to be that big, so it's not that big of a deal, which is why you don't see it on any real file system. But that's the idea towards it. So any questions about that? First real one. All right. So if this sucks, is there anything I can do that's better? Yeah.
Like, I guess you can like kind of like combine both of them, or like if you have like some memory that you can have like as contiguous, you just use that until you can't, and then you like have a pointer check next.
Yeah, I could make it a bit better and like have linked list to contiguous blocks. Might be somewhat complicated, but it would work. It would probably be a bit better. What about if I just go completely out of the box and be like, well, this is based off linked lists, and linked lists suck. What do computers like more than linked lists? They don't. What are hash tables? Arrays. Hash tables are just, yeah, hash tables are actually just arrays with smaller bounds. Hash tables are actually just arrays. We like arrays. So we could do arrays, and arrays would be better. Oh yeah, so, sorry. For file allocation table, similar to linked allocation, just it's fast. So that was our idea, to increase random access speed. Instead of having linked lists, I could just essentially have an array and kind of flip the problem. So I can use a block, and in that block, well, I can have an index for every single block of that file. So in this case, this red block, I'll just store pointers in a row that represent this file. So I'll take this red block, and then to represent this green file, this is just a giant array. So block 0 of this file points to block 0 on the disk. Block 1 of this file points to block 6. Block 2 of this file points to block 2, so on and so forth. So now I transform it into an array. And how big does this array need to be? kind of, yeah. Sorry? Yeah, the number of blocks that are being used for this file. So it's only as big as it needs to be for the file. This will become somewhat familiar to you because it actually uses the same idea as page tables. It looks kind of similar, right? Blocks kind of look like pages, and this kind of looks like a smaller page table that fits on a page, right? So in that case, that's exactly what this is. So it could use an entire block and just fill it in with pointers, and they'll be indexed in the correct order, and they can just point to individual blocks. And this is something called indexed allocation, basically just an array. So has all the same advantages, so files can still grow and shrink because we're just pointing at blocks. We're just, instead of using a linked list to keep track of it, we're using an array. And now we have fast random access. We don't have to keep on going, following the next pointer over and over again. We just, if we want block 2 of the file, we go to index 2, and then it points directly there. We don't have to do any mussing around. But the file size is going to be limited by the size of the block. So right now, I'm just assuming that I'm using one block, just full of pointers. So given that, let's do a bit of math. So if I have this scenario where my index block, all it does is store pointers and nothing else, so it just stores pointers to blocks, and each block is 8 kilobytes in size, and a pointer to a block is 4 bytes, well, what is the maximum size of the file that can be managed by this index block? All right, yep. Sorry? 2 kilobytes. Close. So that 2 to the 11 is how many pointers could fit on a block, right? And then if each of those pointers is pointing to a block, how big's a block? Yeah, so I can point to that many 8 kilobyte blocks. So I'm bad at math in my head, so let's see. So our block size here is 8 kilobytes. So let's just write in powers of 2 because we should be somewhat used to that right now. So that's 2 to the power of 13. 4 bytes is 2 to the power of 2. Thankfully, they are both in bytes. So if I want to figure out how many pointers I can fit on a block, well, I just divide them. So it's block size divided by pointer size. So that means I can fit 2 to the 11 pointers per block. So now if each of those pointers can point to a block and the block size is 8 kilobytes, that should mean the maximum size of the file could be 2 to the 11, so the number of pointers, times how big the block is, which is 2 to the 13, which should be 2 to the 24, or otherwise 16 megabytes. So that would be the maximum size of the file if we did that. Are we pleased with that? Would we like a file system where you can't do anything bigger than 16 megabytes? No, probably not. So we will tackle that in the next question, or next lecture. But guess what? If this was page tables and I wanted to access more virtual memory, what would I do? Yeah. Yeah, more levels. So that's, spoiler alert, that's going to be the same idea we use if we want to make this bigger, but there's going to be some different trade-offs here. So if we wanted to, we could, instead of pointing to a block that points directly to the blocks we use for the file, well, it could point essentially to like another level of index blocks, and then we can make our file way, way, way way bigger. So any questions about that? Again, we'll get to that later. So no questions. All right, so now we have file systems. Help enable persistence. So it's actually how you describe files on your actual physical drive. Your drive only cares about blocks or pages. Terms are generally interchangeable. So API-wise, right, we can open files, change the position. So we learned about the position today, which is in the global open file table. And each process has local open file table entries, which are basically what the file descriptors are. Sometimes it's important to know whether you're sharing global entries or not, because that means you're sharing a position. And when we're actually laying out files on an SSD, well, there's multiple allocation strategies we could use. Contiguous, which is fast but kind of a pain. Linked, which is good because it got rid of that external fragmentation, but it was slow. So FAT was just a faster version of it, where we just crammed all the pointers together. And then indexed, which is basically the same idea, but instead of a linked list, we used an array. So with that, just remember, pulling for you, we're on this together.